Okay, sorry for the interruption. Talking about center of mass when you're jumping upward, for example, um, and this equation that we've been given here. So your velocity of your center of mass tells you everything about how high you're going to jump. And you can actually use that velocity, that initial velocity, to calculate your kinetic energy as well. And that will turn into your potential energy, of course. Use that to calculate your height if you'd like. And the power, of course, is going to be your kinetic energy divided by the time, which would also be the potential energy at the top of your jump divided by time. And so you can see here we have 3.5 times 10 to the 2 joules divided by 0.25 seconds it takes to jump. But those are all good things for your homework. I think that you'll have one or two problems there where an object is either thrown upward or jumps upwards, has an initial velocity, and you can use that to calculate the height. Okay, so 5.7, work done by a varying force. So what happens if the force is not constant? Well, we've seen things like this before. For example, the work that a spring does was a force that varied linearly. And we start doing the sum we start essentially adding up all the area underneath the curve of the force versus distance graph. And that's what they're kind of showing here with the spring. You have a force that you have a force that increases as the stretch length increases, and you get the area under the curve, which is that triangle, and that's why you get the 1/2 in the equation for the applied force of a spring. Right? And they do that. They do the example for the work required to stretch a spring, which of course we've done before. That's no big deal. Other things that vary can have all kinds of different curves. So what if we have this kind of a force curve right here, where it's kind of straight, kind of linear like a spring, but then it kind of bends over as you get here, or it bends over more extremely. Well, it's still just area under the curve, and if you have a graph that has like graph paper here, you can count the boxes under the curve, and any of these triangles here you can kind of count as half boxes and kind of estimate how many watts of energy are being used up here. So that is the end of chapter 5. Let's go take a look at the homework really quick. So look at 5.6. In 5.6 we have only two problems. Electric motor model train accelerates the train from rest to 0.54 meters per second in 16 milliseconds. So of course they've given us a final velocity, they've given us a time, and they're also going to give us a mass. And I think that we're going to need to use a kinetic equation in there, but we can do that because if we can find the acceleration, then we can figure out the force, and we have then the force and the time. We'll just need the distance, right? So then we can also use a kinematic equation to find the distance. So two kinematic equations from the last chapter maybe to find your acceleration and your distance traveled. Then you can use force times distance to get your work, divide that by the time that they give of 16 milliseconds. That's 10 to the minus 3 seconds. And you're good to go. Second one, you have the mass of an elevator, moves upward 2.5 seconds, constant acceleration until it reaches cruising speed. Again, you're going to probably have to use some kinematic equations for this final speed and this time to find the acceleration. You'll multiply that acceleration. Well, you have to add to that the gravitational acceleration, which the elevator is going to have to overcome, and then multiply that total acceleration times this mass to get a force. Use that force. Also use a kinematic equation to find distance. You're going to have to use kinematic equations a few times here. But that's not uncommon because you often need distance, force, and time to do work, or to do power equations. And the last homework assignment, 5.7, is going to be fairly simple from what I remember. We just have essentially things that we're going to count boxes underneath the curve, right? Now be aware that when you're counting boxes above a curve, because really what you're going to do is you're going to count boxes between the curve and the x-axis. But when you have something like this goes below the curve, those are going to count as negative work. So negative boxes, you take these boxes, add these boxes, you get the total work done. So these boxes, take away these boxes, or subtract these boxes. Okay, well, that one seems to be fairly straightforward. I think I'll be done with that. So that is the end of Chapter 5. If you have any questions, please send me an email, and I will get back to you as soon as I can. Goodbye.